batch 1, you did rational expressions, and you had to state non-permissible values. You don't have to write any of this. I'll tell you what to write when you want to. You can write the title, but that's about it. So non-permissible values occur when you have variables in the denominator. So when you have variables in the denominator, you have a chance of your denominator equaling 0, correct? And we can't have our denominator equal 0 because we can't divide by 0. So the moment we have any type of variable in our denominator, we have to state non-permissible values. Now, instead of having like x plus 3 in the denominator, we're going to have like sine x in the denominator. And we'll have to state all the places where sine x equals 0 and say it can't equal that. We can't have it equal to 0. So we're going to look at some examples. Say we look at the reciprocal identity cosecant. Cosecant is 1 over sine x. We agree? If you forget, you could look on your formula sheet. Secant is 1 over cos. Cotan is 1 over tan. Tan is sine over cos. Cotan is cos over sine. These are all on your unit circle. So it's not like you have to memorize them. They're on your unit circle, on your formula sheet. They are on the formula sheet. You don't need to memorize them, but you do need to know they're there, or you don't even know to go to your formula sheet to take them off. Okay? So you don't have to write these down. They're on your formula sheet. But we are going to go ahead to these ones. Okay. So we have to determine the non-permissible values of x for each of the following. So we have sine x over cos x. And non-permissible values only are a problem when we have x in the denominator. So the first thing we want to do is always turn our equations, if we can, into sines and coses. Well, this equation already is in sine and cos, correct? So if it was in secant, we turn our secants to 1 over cos. If it was in cosecant, we turn it to 1 over sine. So we turn them into sines and coses if we could. Okay? This one already is. So the only denominator we have right now is cos x. We agree? So we have to state all the places where cos x cannot equal 0. All the values of x that would turn that denominator into 0. So for example, if I put cos of 90 into my calculator in degree mode, it would give me 0. So if I put in 90, cos 90, I would get a 0 in my denominator, would I not? And what can I not have in my denominator? 0. So we have to state all the values of x that would cause that denominator to turn into 0 and say that it can't be those. So cos is just x, is it not? Where does x equal 0? Pi over 2 and 3 pi over 2, or 90 and 270, right? And every varying level in between that, positive and negative, right? So when we state non-permissible values, we're actually stating general solutions. So when we state general solutions, we say our first positive. What's our very first smallest positive value we have where it would equal 0? Where does cos x equal 0? The smallest positive. 90. So we'll say 90 degrees. Remember when we do general solutions, we state the smallest positive, and then we add to it how long it takes to get to the next one. 180 degrees, right? N, NEI. So therefore, we filled in any integer in for n, we'd get any solution that could cause us to have a 0 in the denominator. So our x cannot be any of those. And we're going to write it in radians. And we'd be done. So any varying level of 90 and 180 onwards this way or in the negative realm, if I type that into my calculator, it would get me a 0 and I'd have a 0 in the denominator. What's wrong with B right now? Is it in coses and sines? No. Can we switch tan to coses and sines? We would get cos x divided by what? Sine x cos x? Sin x over cos x, sorry. What did I tell you to do when you have full fractions? Write them beside each other. So we're going to get cos x times cos x over sin x. Or, I shouldn't have skipped the step. I'll lose people. I'm going to go cos x divided by sin x over cos x. What happens with the division? The second side flips. We agree? So remember rationals when we did division? We stated non-permissible values of the denominator over here, which is just 1. Is there a variable in it? No, so it's not going to get us non-permissible values. And we stated both the right-hand side. Why? Right now, cos is in the denominator, but when I solve this, I'm going to multiply, and what's going to happen? It's going to flip, and when it flips, sine's going to be in the denominator. So anything that has been in the denominator or will be in the denominator, we have to state non-permissible values for. So that's why when you divided rational expressions, you stated non-permissible values for either of these. Okay? So we are going to have to state non-permissible values for when sin x cannot equal 0 and when cos x cannot equal 0. Where are the places that would get sin x equaling to 0? 0 and 180. Where are the places where cos x would be not equal to 0? 90 and 270. So we could state separate solutions. For this one, we could say, for the sine one, x cannot equal, what's my first positive? 0 degrees plus 180 degrees n NEI. But what did I tell you don't state? The 0. So we would just say pi n NEI, right? And what about the cos x cannot equal 0? We already stated it, right? It was pi over 2. It was this one. X cannot equal pi over 2 n, or sorry, pi over 2 plus pi n. And that's great that we have 2 solutions, but on the diploma, they'll give you 1. Because instead of writing these out separately, they combine them. So, sin x cannot equal 0 here and here. We agree? Cos x cannot equal 0 here and here. How could they just combine it as one general solution? So what would be the first positive, though? Not 90. The first positive would actually be 0. So this one I could combine with x cannot equal 0 degrees plus 90 degrees n NEI. But instead of writing the 0, they wouldn't. They would just write it as 90 degrees n NEI or pi over 2 n NEI. And it would get every single answer. So when you have a non-permissible value of cos x and sin x, it's every single quadrant. Every single one. So you can just write it as pi over 2n. Because it's cos and sine. What's up with C? Yeah. You have a cotan, so we need to change that to what over what? I feel like we're on a beach, but not with that bird. Okay, it's cos over sine, cos x over sine x. Would I go divided by and down here? It's a fraction, so I would divide it next to each other. This would be technically over 1. Would the 1 get me a non-permissible value? This 1 down here? No, it's just a 1. It doesn't have a variable. So my non-permissible values are going to happen where sine x cannot equal 0. And what else? One plus sine x cannot equal 0. So it would be sine x cannot equal -1. Remember, we always have to solve for the trig. And now we have to give the solutions. So if you haven't noticed, just solving all of these is trig 1. So if you can't solve, you can't even do these questions. You need your trig 1. So where does sine x equal 0? Where y equals 0? Where does y equal 0? Here and here. So my solution is going to be x, oopsies, x cannot equal pi n NEI. Why didn't I give a positive solution before I put pi n? What's my first positive solution? 0. And we don't write 0 plus. It doesn't change anything. Where is sine x equaling to -1? So where is y equal to -1? 270. 270 is what in radians? Yeah, so x cannot equal 3 pi over 2. Plus, how long is it going to take me to get back there? 2 pi, or 360. But we're in radian measures, so we have to write 2 pi n NEI. And these are separate solutions because I can't put them together. I could only put the sine and cosine together because they hit every quadrant. You guys tried D. So, tan x and then cos x minus 1. Tan x I'm going to first change to sine x over cos x divided by cos x minus 1 over 1. So I have to state non-permissible values for the cos x, for the cos x minus 1, and technically for the 1, but the 1 doesn't get me any non-permissible values, right? It doesn't have a variable. You need a variable to get non-permissible values. So we have to state where cos x cannot equal 0 and cos x minus 1 cannot equal 0. So it's just going to be where cos x equals 1. You need to solve it. So cos x equals 0 when x equals 0. When does x equal 0? On the y-axis. So x cannot equal, my first positive is pi over 2 plus, it repeats itself every pi n NEI. That's my one solution. The other one is where cos x equals 1. Where does cos x equal 1? When x equals 1, which is here. So 0 plus 2 pi n NEI. Do I write the 0? So x cannot equal 2 pi n NEI. Those are your two solutions. So the first step is always to change them to cosines and sines where possible. Okay? And then you'll see where you actually have non-permissible values or not. If you have these printed, we're going to go back a page to verification. So what we're going to do is verify by a calculator, y1, y2, that something is correct. But we're also going to verify by if we plug in a value, does the left side equal the right side? But verifying one value, does that show that it's a proof for everything if it just works for one example? No. What if it works for 100 examples? Does that prove that it works for everything? No, that proves that it works for 100 examples. So the only way you can prove that something actually works, which is what we're doing tomorrow, and the only way you can prove that something works is if you prove that for the left side and the right side, by not plugging anything in for theta, I can get them to look the exact same. So I'm going to use formulas. That's what we're going to do tomorrow. Today we're going to verify. Verify means it works for this example, but that's not saying it works for everything. So the first thing we're going to write out is our Pythagorean theorem identities. Our Pythagorean theorem formulas are these ones here. These three. Sine squared plus cos squared equals 1. 1 plus tan squared equals secant squared. 1 plus cotan squared equals cosecant squared. And we're going to write all the varying levels of it. So we have cos squared theta plus sine squared theta equals 1. Perfect formula. But what we know about formulas is they can be rearranged, right? Like the distance equals speed times time formula, we could always rearrange it depending on which one we were looking for, time or speed or distance. All of the formulas on your formula sheet, you guys need to remember, can be rearranged. It's not always like it has to be cos squared plus sine squared equals 1. What if we have cos squared? If we have cos squared theta, we could replace it with 1 minus sine squared theta. We can move the sine squared theta over, can we not? So if I had a cos squared theta in my proof, I could replace it with 1 minus sine squared theta. Because I can rearrange this formula. We agree? What if I had a sine squared theta? I could replace it with 1, move the cos squared over, minus cos squared theta. Every formula on our formula sheet can be rearranged. Everyone forgets that, though. They just look at that in the exact same form that it is. But every formula can be moved around. Just like any formula you've ever been given can be moved around. The next one is 1 plus tan squared equals secant squared. So that's great. If you're given secant squared theta, you could replace it if you wanted to with 1 plus tan squared theta, right? But we can rearrange this formula. What if we were given tan squared theta? We could replace it with secant squared theta what? Minus 1. What if we were just given 1? We could replace 1 with secant squared theta minus tan squared theta. All of these formulas can be rearranged. Our last one is 1 plus cotan squared theta equals cosecant squared theta. So if we were given cosecant squared theta, we could replace it with 1 plus cotan squared theta. Indirectly, if we were given 1 plus cotan squared theta, we could replace it with cosecant squared theta. Could we not, interchangeably? So often, if you have something like 1 plus cotan squared theta, you'd replace it with cosecant because cosecant's more simple, right? We want it to be more simple. But what if I had cotan squared theta? I could replace it with what? Or if I had 1, I could replace it not only with this, or not only with cotan squared theta plus sine squared theta, I could also replace it with cosecant squared theta minus cotan squared theta. Or, more so, if I had cosecant squared theta minus cotan squared theta on my formula, like on a proof, if I had cosecant squared theta minus cotan squared theta, I would know, hey, I can just cancel that off, it's a 1. I could make it more simple like that. Because I know that the formula can move around. Okay? So we're going to do some verifying at the bottom. So we can rearrange those formulas all around. Any formula on our formula sheet can be rearranged. And we have to remember that all the trig ones can be rearranged. That's a huge thing that we need to remember, because most people think that they're stuck in the way they are. No formula is stuck in the way it is. You can rearrange any formula you want for what you're trying to find. You can isolate anything. So we're going to verify this. We're going to ignore all of this. I'm just going to answer it. So we are going to verify for cos squared theta plus sine squared theta equals 1, which is a formula off the formula sheet. So we know it's a proof. They've proved it. We are going to verify, not prove it though, we're going to verify that if we fill theta over 6, or pi over 6 into for theta, sorry, that we'll get left side equals right side. So we're going to prove using a 30-degree for theta, that left side would equal right side. So we're verifying it works for one thing, not for all things. Not proving it, we're verifying. So I have cos squared pi over 6 plus sine squared pi over 6 equals 1. Do you remember how I told you we could put cos squared theta into our calculator? Because you can't just go cos and then a squared. Because when you press cos on your calculator, a bracket opens, doesn't it? So you can't go cos squared. It's cos bracket. So you have to deal with the fact that it does that. So it's going to go cos bracket. What goes in the bracket? Pi over 6. So you're stuck with your calculator doing that to you. How can you square it? The whole thing in brackets squared. That's how you have to do it, because your calculator won't allow you to put the squared in there. So you have to do the whole thing squared. Then plus sine, it's going to open a bracket, pi divided by 6. The whole thing squared equals 1. So that's the only way you can do these when they're squared. The whole thing squared. Now, it says what? Using exact values. So for the people who are punching into their calculator and getting a decimal, is that helpful? No, because I don't want decimals. I want exact values. So where am I going to have to turn to get exact values? The unit circle. Exact values come off of your unit circle. So when you are doing trig 2, you should have two things handy at all times. Your unit circle and your formula sheet. Handy at all times. So I go to my unit circle. I go to cos pi over 6. What is that? I go to pi over 6 and I want the what? I want the x, which is square root 3 over 2. So this whole cos pi over 6 gets replaced with square root 3 over 2, but it's still squared. Plus, what's sine of pi over 6? I go to pi over 6 and I take off the y. And what's that? 1 over 2, but it's still squared, equals 1. So when you're doing proofs or you are verifying, you're verifying that left side equals right side. So nothing on the right side is going to get moved to the left side. Nothing on the left side is going to get moved to the right side. So this equal 1 will stay equal 1 the whole way down, because I can't move anything to it. And that's all that's there. So when you verify or prove, you do not cross over the equal sign. You work your way down the left side, down the right side. It's like a check. Remember how when you solved in grade 9 for the first time for polynomials and you had to distribute in and you got x by itself, but your teacher said, hey, you can take that and you can plug it back in and you can know at the end of the test whether you got that question right or not? Or when you did rationals in grade 11 and you solved a rational, you could plug it back into the left side and the right side and see if your rational was correct or not, whether you should be happy or not very happy. Same thing here. We're just checking these. Verification is a check. So everything on the left side stays on the left side. Everything on the right side stays on the right side. When I square this, I square a square root. So square root of 3 squared is just 3 over 2 squared, which is 4, plus 1 squared, which is 1, over 2 squared, which is 4, equals 1. What's 3 quarters plus 1 quarters? 1 equals 1. So what we need to write then at the end here is we need to go LS equals RS. Left side equals right side, and we verified it. Have we verified it? So now it's a proof. It's proven for everything now because I checked pi over 6 and it worked. Right. It's not proved for everything. It's proved for this. It's not proved at all, actually. It's verified. Right? It's verified that pi over 6 works in this equation. I verified one value. Now, if I verify a million, it's a proof. No. The only way you can prove a proof is not fill anything in for those thetas and get left side to equal right side. We can fill in formulas. We can't fill in values into theta. So this is a verification. And we have to know how to verify. They have to be able to ask you how to verify. So example 1 here. They want to know, is cotan x sine x equals cos an identity? Well, doing any of these methods, we're not actually proving that it's an identity at all. All we're proving is that we can verify it for 2 values. And if they both work, yay, it works for 2 values. Woohoo! So we think that we should be able to prove it. But we're not proving it at all, we're just verifying. So we're going to do B first. Evaluate both sides for 45 degrees. So we're going to fill in 45 degrees. So we have cotan of 45 degrees, sine of 45 degrees, equals cos of 45 degrees. Can we flip angles? No. Oh my goodness. No, we cannot flip angles, but we can flip answers. Cotan 45. We go to 45. Remember, if we go to 45, we can pull cos and sine off really, really easily. Cos is x, sine is y. We have the answers to that. So let's fill those in first. We'll leave this one out for now. Sine of 45 is what? Go to 45 and take off the y, which is root 2 over 2. And you replace the whole thing. Equals cos of 45. What's cos of 45? Root 2 over 2. Cotan is what divided by what? Cos is x divided by y, or cos over sine, right? So we're going to do cotan of 45 off to the side. Cotan of 45 is cos divided by sine. What's cos at 45? Root 2 over 2. Divided by sine at 45. Root 2 over 2. What's my actual answer? 1. Remember at the 45 degree reference angles, cotan and tan are 1 or negative 1? And we've proven it, well, we've verified it, I shouldn't use proof. 1 times root 2 over 2. We verified that left side equals right side. Why is pi over 3 harder to verify? Because cotan 45 is not 1. It's a fraction. Cotan of pi over 3 is not 1, sorry. So we go cotan of pi over 3, sine of pi over 3, equals cos of pi over 3. Cos of pi over 3 and sine of pi over 3 are really easy to pull off of there because they're just the x and the y at pi over 3. We agree? So sine of pi over 3 is root 3 over 2. Cos of pi over 3 is a half. They're at the 60s. Cotan of pi over 3, I'm going to do down here, is cos divided by sine. So it's a half divided by root 3 over 2, which is a half times 2 over root 3. 2's cancel. It's 1 over root 3. And then I rationalize my denominator, so I multiply by root 3. So if you didn't know that you should be excited when it's a cos or a sine, you should, because cotan's a heck of a lot more work. Even a secant or cosecant's not too bad. because a secant is cos flipped. A secant is cos flipped. A cosecant is sine flipped. You might have to rationalize the denominator, but all they are is the answers flipped. Cotan and tan, you actually have to do the work. So in for cotan of pi over 3, I'm going to put root 3 over 3. When I multiply root 3 times root 3, I get 3 over 6 equals a half. Now, so many people will write left side equals right side. Really? Really? 3 over 6 equals a half? If you showed this to a grade 1 kid, if you showed this to my daughter, she'd be like, Mom, 3 over 6 does not equal 1 over 2. A 3 does not equal a 1, and a 6 does not equal a 2. Would that be true? Like, if you didn't know what those numbers meant, does that look real? 3 equals 1 and 6 equals 2? No. But if I go 1/2 equals 1/2 and I reduce it, now, no matter who sees this, believes it, right? You could show this to your parents. You'd be like, a half equals a half. And they'd be like, yeah, no doubt. Yeah, that's true. This, you would assume that most people would do that, but they wouldn't. And to verify, you have to show that the left side equals the right side, if not, you guys, I could go, yes, you're saying, oh, most people know 3/6 equals a half. Yeah, well, some people know root 3 over 3 times root 3 over 2 equals a half. Left side equals right side. Then assuming that they know this is correct is assuming the same as if they know that's correct. We agree? This is just easier. Cool. Can someone close the window? Now, I want to show you on a graph. So we can verify this with a graph. So we have cotan x sine x equals cos x. We can do any verification of this. So I could divide by sine x too. But I'm going to treat this as a y1, and I'm going to treat this as a y2. The only catch is I don't have a cotan button. So I'm like, how do I type cotan into my calculator? And I should instantly think, look at because you did it, your formula sheet. If you're stuck, look at your formula sheet. It's there. It tells you. So we're going to go 1 divided by tan x times sine x in our y1. And our y2 is still going to just be cos x. And we're going to see if they look the same. Now remember, this doesn't prove that it works for everything. This just verifies that it could possibly work. Oh, where did my calculator go? Okay. So, in y1, we're going to go 1 divided by tan x times sine x. And then in this one, we're going to have cos. And then it doesn't matter what mode I'm in. I'm going to go zoom trig. Now, I have different colored ones. So I have a blue and the red goes on top. If you look at that, the red is a solid graph, is it not? The red represents a cos graph. If I take the red graph off, I actually have this graph here. What's different in this blue graph than the red graph? And it doesn't show up on most of your calculators unless you have the colored ones. What's the difference between the blue and the red? Yeah. Right. So this one has little gaps. All these little gaps are non-permissible values. So if you typed it into your calculator, you could see the non-permissible values. Now, some of you can't see the gaps, but if you went second table, it would show undefined beside those x values. So you would know that it doesn't exist there. Okay? Now, if you're someone who doesn't have a colored graph, I could physically see that my colored graph drew over the other colored graph, right? But if you don't have a colored graph, remember you need to make the second graph thicker. So you can see a thin graph drawn and a thicker graph drawn on top of it. We agree? Because if not, what you do, which scares me, is you will have the thin graph drawn. And then you will just see, hey, there's one graph. And you're like, boom, They're on top of each other, we're good. The graphs are the same, except your other graph is actually floating on top of the window that you can't see it, but you don't actually know it's floating up there because you didn't make your graph thicker and you don't see the floating above or below graph. Okay? So always make the second graph thicker so you can physically see it actually drawing, not that it's off your window and you assume it's drawing on top of the other one. Okay? Your homework is this, the blue box.